This is the ESP32 development board by Espressif. The ESP32 is a quick $10 US way of Wi-Fi enabling any project you have. In this video, I'll show you guys how to set up the ESP IDF or IoT Development Framework and use it to get an LED blinking on the board. Okay, so to get started, you're going to Google ESP IDF, that's the IoT Development Framework. It should bring you to this GitHub repo. This has a bunch of examples and the build chain and pretty much everything you need to set up your ESP32. You're going to copy this link in your command line. You're going to git clone tactac recursive that directory. What the tactac recursive does is if there are any submodules in this repository, which means a submodule is another Git repo inside of a Git repo. This repo has a bunch of those, so it'll go into every sub repo recursively and clone those in as well. So you want to do that. There is a lot of stuff here, so this will take a second for you guys to get through, but we'll let this run and we'll come back. Okay, great. So for me, that took about 3 minutes. I hope it took not that long for you. But now that we have that here, we can go into the ESP IDF folder and ls to directory. A bunch of files should be here. We don't really care about a lot of these right now, but the big one we want to run is install.sh. So install.sh will actually go through, it'll install all of the required apt repositories, all of the required pip repositories, and everything we need, and set up our environment so that we are able to run idf.py, which is the framework itself. So let's run this. Cool, so this didn't take very long for me because I already ran this before I started this video. It may take about 10 or so minutes for you because it has to go through and pip and install all of these repositories. But once this has ran, now we have this export.sh file. So what this export.sh file is, it'll export environment variables so that in the current window that we're in, we're able to use idf.py. So to run this program, we do dot for the current directory and then export.sh. So here you see that it's adding the ESP IDF tools to the path, and now we can use the idf.py. So this is where a lot of the money comes from with the IDF, right? So I'm gonna make a directory for all my projects, and then we're gonna go into there, and then I'm gonna type idf.py. So this is all of the different things that IDF is able to do for us. The big one we're going to do right now is create project, because we want to make a new project from scratch that will allow us to blink the LED on my ESP32. So we're going to go idf.py, create project, and then create project wants us to give it a name. So we're going to say idf.py, create project, and it's going to be blink LED. Cool, so now we have a folder called Blink LED, and you see they have the CMakes file and a main folder. So IDF does generate CMakes files, which is pretty cool. It's a pretty robust build system. We're gonna go into main, and then we're gonna sublime main, right? Because we wanna get our code all set up. Cool, so this is what it gives us. It gives us a shell that we're able to write our program in. So what's actually happening in the background that we don't get to see outside of main is the board is running FreeRTOS. FreeRTOS is an operating system that runs code as tasks, right? So we're able to specify a task for the LED blinking, a task for the Wi-Fi scheduler running, and all these other things that are happening. And then every couple of system ticks is what it's called. So for example, maybe 1,000 clock cycles, the scheduler runs and it decides what thing goes next. And then one of our tasks that run on the OS is our application, so application main. So what we can actually do to build this is go to the top level directory where the CMakes file is, and then we do idf.py set target. So right now no target is set. I have an ESP32 board, so we're going to set the target to ESP32. And what it's doing here is it's configuring our build files to enable it for the ESP32. And then once we do that, we do idf.py build. So this takes a very long time because what it's actually doing is compiling every possible feature that you could have put into your project and setting it up so that it'll run faster in the future. So this initial compilation does take a few minutes, but once this stops, every time we make a modification, we only recompile our application, not the entire OS. So we'll let this run for a second and we'll come back. Whew, there we go. Okay, so that took about 5 minutes for me. Hopefully it takes a little less time for you, but it does take a minute, but there's a lot of code getting compiled there. So this code starts as an application as a task in FreeRTOS. And the way that we can actually prove that is we can have the ESP32 print the name of the task that we're in to the serial console. So the way that we do that is with a few things. First, we're going to have a variable named our task name, and it's going to be equal to PC task get name. This a little bit. So that's actually a function in FreeRTOS that returns the name of a specified task. And if you give it a null handle, it'll actually go into the task that's calling it, so our task, and get you the name of the task. And it puts it to this character, or to this pointer. And then we can do ESP log, which is a function that writes data out to the serial console on the ESP32. And we're going to make the first argument what's called the tag, or it's like the caller of the log when it outputs it. And then we'll say, hello, starting up. And then that'll be it. We'll end it there. So this is all our code is going to do for right now. And then just to prevent a possible crash for not exiting a task properly, we'll just sit here in an infinite loop. So the way that we build this is simply by IDF build again. And you should notice that it takes significantly less time to do this. We are going to get a few errors though. Yeah, the reason we're getting errors is we didn't give it the header files for the FreeRTOS task API and for the ESP log. So the way we do that is pound include FreeRTOS, FreeRTOS.h, and then pound include FreeRTOS task.h. So this is the FreeRTOS OS API. This is the FreeRTOS task handling API. And then we also include ESP log.h. If you're curious where I'm getting all of this from, you actually can go and Google ESP32 development information, and it exposes the API of where all of these functions come from. And then down here, you can see how to use this library. It shows you that you have to include ESP log, and this is how you use the function. So ESP log, I misspoke. We actually have to do ESP log I for information. I apologize. So ESP log I. Cool, so then we can build this again. Notice that nothing is rebuilding, it's only our program that's rebuilding. And we get no errors, which is great. So now we have to flash this thing to the board. The way that you flash a program to the board with ESP32 is you do idf.py tac-p the port. So for me, it's dev t2i USB 0, and then flash. What it'll actually do is it'll reach into your configuration settings. It knows what binary to flash, and it'll go to flash the program to your board. So we go here, it'll try to recompile it and get it all set up. And then for me, I have to go over here and hold the boot button for this to actually catch. Cool. And now we can see that it's uploading our program to the board. Okay, so now we have stuff that we want to see being output to the serial console. We need to do idf.py monitor. This will actually go in and grab the serial console on the device. And again, I'm holding the boot button for it to catch. Now it's in a give me data to program mode. Now I just hit the reset button. And now this is the output of FreeRTOS starting up. So we have it loading up the SPI flash, and then it's going in, it's setting up all of its heap segments and all this other good stuff. And then eventually it runs. And we say main, hello starting up. That's us. And then the board actually crashes. So what happens is we put the board into an infinite loop in a task without, it's called yielding the task to the scheduler. The watchdog timer of the board saw this and it crashed the board. So we're actually seeing a huge crash dump of the board, and it's going to keep doing this over and over again because the watchdog timer is complaining for our task not basically giving priority back to the board. So the way we can do that actually and fix this is we can do v task delay, and we'll do 1000. This is actually wrong. We'll talk about why that's wrong in a second. But again, we builds the whole thing. We flash, and again, I have to hold the boot button for this to work. Let it flash. And then we do the monitor. Hold the boot button again for it to catch, and then reset. And now it's starting up, and now this task delay is yielding priority back to FreeRTOS, and as a result, FreeRTOS is not complaining. So to get the GPIO running, right, the whole point of this tutorial is to get this LED to blink. We need to do a few things. First, we need to pound include the GPIO driver. This is the code that runs the GPIO devices on the board. Without this, the program would yell, or the compiler would yell at us for not knowing what a lot of these functions do. So first, just like an Arduino, we need to set the direction of the GPIO pin, right? So we're going to set the direction of blink LED, and blink LED is going to be defined as pin 2. Set the direction of the blink LED to, I think it's GPIO out. And again, I don't know the actual name for what the output is, so I can actually just go here and I can do GPIO set direction, the function, because I know that's the function name. It will show me the function in the API, and then I can actually look at what the proper number is. So GPIO mode T has these, so it's GPIO mode output. That was close. Cool. So now that we have the direction set, we also want to just GPIO reset pin on blink LED. This just flushes any config functionality or config settings that may already be on the pin, just in case something got changed in the OS before it got to us. We want to make sure that all of that goes away. Okay, great. So now we do GPIO set level on the blink LED to high. We're just going to do 1. And then GPIO set level blink LED to 0. And then just like in my FreeRTOS tutorial, we're going to do V task delay 1000 for 1 second. And what this does is this actually sleeps our task and yields priority back to the processor so we can do other things in the background. Cool. So now that we have this written, in theory, what are we going to do? We're going to print hello starting up, reset the blink LED pin, set the direction to be an output, set the level high, yield to the processor in sleep, set the level low, yield to the processor in sleep. Cool. So to get out of our monitor, by the way, we do control right bracket, and we're going to build. Fatal error with GPIO driver. What is the proper... Oh, it's driver/GPIO.h, excuse me, not driver. Here we go. Driver/GPIO.h. Okay, build again. Cool, so then we go to flash it. And again, I have to hold the boot button for this to work. Flashing, good. And then we go to monitor. Okay, so we get this weird bug where the board does not actually flash every 1 second. It flashes every 10 seconds. We'll wait for it to go down to see that it's working. Okay, so something's happening, but it's not the right thing. Why is that? So funny story, I actually ran into this when I was setting up this tutorial. V task delay does not delay for a number of seconds. Excuse me. V task delay delays for a number of clock ticks. So a clock tick is not a clock cycle. A clock tick is a number So what VTask delay does is it actually sleeps for a number of sys ticks, not a number of actual seconds. So we need to actually divide this number by the conversion rate of sys ticks to milliseconds. And that conversion factor is called this, port tick period milliseconds. So what it does is it converts 1,000 milliseconds, which is 1 second, what we care about, and it converts that to the proper number of sys ticks so that the VTask delay actually delays for only 1 second. So we're going to add that to both of these. And again, control right bracket to get out, and then we IDF build. IDF flash. Flashing it. Great. And now we have the board flashing 1 time every second. In the next video, what I'll do is I'll actually build out the code that Wi-Fi enables the project and connects you to your wireless network, and it will call out to the internet and report the temperature of CPU core 1 every time it changes. But with that being said, I hope you guys learned something. If you did, do me a favor, hit like, hit subscribe, and I'll see you guys in the next video. Take care.